All right, so we're going to move into Chapter 5. This is the last chapter that we'll do in this class. How sad. Anyway, we want to approximate area under curves. This is going to actually be a really important idea. It's going to relate to the antiderivative stuff that we just started talking about in the last section. So to just get an idea of why this might be important, if we consider a car that's traveling at a constant velocity of 60 miles per hour over the course of 2 hours. If we look at the area under that curve, so actually I'll draw this. So if I say, okay, here is my XY coordinate axis. On the Y-axis here I have the velocity, and then here would be time measured in hours. And then here, velocity would be miles per hour. Oops. And then what this is, if we're driving at a constant velocity of 60 miles per hour, that means we just have a flat horizontal line here at v equals 60 miles per hour. If we want to find how far we've traveled, we can actually look at the area under this curve. So if we've traveled for 60 miles an hour for 2 hours, if I look at the dimensions of this shape that I've drawn right here, this right here, this is a total of, and actually probably easier to look down here, this is a total of 2 hours. So this is, here, let's do this, 2 hours. And if I look at the velocity at the height over here in miles per hour, this height over here, we said we were traveling at 60 miles per hour. So if I was to multiply these two together, 60 times 2, that would tell me two things. First of all, it would tell me how many miles I've traveled. It would tell me my total distance traveled, in this case, my displacement. But it also tell me something more interesting. Remember, this blue line right here really represents a function, and this would tell me the area under this curve over this interval. It seems silly because we just multiplied two numbers together. It's just length times width. But that is the area of a rectangle, which is the shape that we have right here. So if we graph the function, we look at the area under the curve. This represents the total distance traveled or displacement. But the problem is that we're not always traveling at a constant velocity of 60 miles per hour. What if our velocity changes over time, right? There's going to be times when we need to slow down, times we need to speed up. So your velocity function, it might be all over the place. Might hover at some point and then go down, and then your velocity function is just not going to be a straight curve most of the time. 99.999% of the functions, the vast majority, almost every single function we look at is not constant. At least all the interesting ones aren't. So we need to think about how we can look at area under curves here. So we're going to use this idea, though, of, let's actually draw something like this. So here's my function, let's say. If I want to estimate the area under this curve over this interval that I've drawn, let's call this A and this B. Trying to find the area under this curve it's a hard question. It's not something that we're prepared to do. So in math, when we come across a question that we don't know how to answer, we say, okay, how can we get an approximate answer using stuff that we already know? And then maybe we can improve that approximation. I gotta have a starting point. Think about this shape that we just drew back here. We drew the shape of a rectangle. I know how to find the area of a rectangle because the area of a rectangle is just length times width. What if I use that same idea down here? You think about, okay, if I build a rectangle, let's build a rectangle. Well, what should the height of my rectangle be? How about here? Here's my rectangle. Well, That's not a very good approximation because I have all of this area that I haven't accounted for. I could find the area of that blue shaded rectangle that I just created, but the yellow shaded region that I just highlighted, that's not being counted. It's a pretty crummy approximation. So okay, maybe we'll try picking a different point. Say oops. Say okay, here's the rectangle. We're going to estimate the area under this curve using the rectangle. Now I have a different problem. All of this area over here that I'm overcounting. My rectangle's too big now. It's bigger than the actual area under the curve. So this is another pretty crummy approximation. Both of these, and we can argue about which one is better, but at the end of the day, they're both not very good. So okay, I'm going to think about how can we take this idea of rectangles. I really like this idea of rectangles. How can we make it better? Well, you could, of course, average the two together or, do things like that, but that's not really going to work out for us in every single case. The idea here is, what if we try to minimize the area that we're either overcounting or undercounting? So what if we drew this rectangle? So let's go back and actually let's compare it to the first rectangle that we drew. We drew in this rectangle. We said, okay, here's our rectangle. What if I said, okay, and that's not very good, but what if we split it up? What if we said, okay, what if we split this up and we find the area of this green rectangle that I am now shading in and this other green rectangle that I'm shading in? You still probably wouldn't say that that approximation is very good because, okay, we've got this area that we're not counting and this area that we're not counting, but you have to admit it's better than what we started with. So we say, okay, what if we added in another rectangle. What if we just add in some more rectangles? I'm going to add in a rectangle here, find the area under that guy here. And I'm going to find the area of this first rectangle that I drew in, and then I'm going to draw in another rectangle right here. So now instead of 2 rectangles, I now have 4 rectangles. Okay, I feel like we're getting somewhere here because now we're not counting this area. We still have some area that we're not counting, but that area seems to be getting smaller. So hopefully we're sensing a pattern. The idea here is if I add in more rectangles, I get a better approximation. So if I added in a bunch of little teeny tiny rectangles, it's still an approximation. It's still not perfect. But in every single one of these cases, if we look at the area that I'm kind of undercounting or not accounting for here, that area is pretty small compared to what we started with. And the more rectangles we add in over that same area, the smaller the area that we're not counting for. So this is kind of the big question that I want to think about here. It says, what can we do to improve our approximation? The idea here, the main idea, is that if we use more rectangles over the same interval, if we add in more rectangles over the same interval, so if we're going from 1 to 2 and we add in twice as many rectangles, we are going to get a better approximation. And at the end of the day, it's still an approximation, but it's better. Right now we're thinking about how can we improve this approximation. And what we're going to do in this section is we're actually going to practice just this process of approximating the area under the curve. And it's going to be a little bit, I think students overcomplicate this. And that's not to say that it's easy, but at the end of the day, keep in mind what we're doing. What we're going to be doing in this section is we're going to be splitting an interval up into a bunch of smaller intervals. We're going to find the area of each one of these rectangles, and we're going to add them all up.